This is Chen Chen. I'm a second-year PhD student at UT Austin. In this presentation, I'll be introducing our work, Relational Graph Learning for Crowd Navigation, which was done in my undergrad at Simon Fraser University in collaboration with Shahu, Payam Nigdal, Greg Murray, and Manoli Sava. Nowadays, mobile robots are playing more and more important roles in our lives, from elderly people's assistants to delivery robots. Navigation is the most fundamental building block, which is challenging due to the safety and social ethic concerns. Intelligent and social aware navigation behaviors require considering complex human interactions. However, prior works failed to handle high-order human interactions. Most of the existing crowd navigation approaches model interactions in a coarse-grained style. They either used an LSTM or CNN to aggregate human states. A recent method addressed this problem by using attentive pooling to aggregate pairwise interaction features, but this attention mechanism only models one-way attention from the robot to humans. Graph convolution network is a powerful tool for interaction modeling, but most works operate with the fixed graph inputs. To address this issue, we propose a graph-based approach that encodes interactions among all agents. This approach can very well deal with complex interactions, such as a group of people walking together, which presents strong spatial connections, and it cannot be handled by previous works. Our contributions are twofold. First, we revisit interaction modeling in crowd navigation with relational graph learning. In addition, our approach also models the temporal evolution of human crowds by leveraging a learned human motion model, which leads to better prediction of free space and paths. Before diving into our approach, let's first look at the problem. In this work, we try to solve a crowd navigation task where the robot navigates through a crowd of n humans to a goal position, and we formulate this problem with DeepRL. Each agent, including the robot and humans, has an observable state, which is its position, velocity, and radius, and it also has an unobservable state, which is its goal position, preferred velocity, and orientation. Each agent can observe other agents' observable states. From the robot's perspective, the state of the world consists of its own full-state ST and all other humans' observable states WT. The learning objective is to find an optimal policy and an optimal value function. The optimal policy maps an input state to an optimal action, which gives the maximum expected return. The optimal value function is the cumulative discounted reward given an optimal policy. In this equation, R is a reward function of an action and state at time t, which penalizes collisions and encourages social aware actions, such as maintaining a comfortable distance from humans. Gamma is a discount factor, encouraging the robot to reach the goal position quickly. P represents the dynamics of all agents, which is an unknown state transition function. Optimizing this equation leads to a policy that navigates efficiently and safely. There are two challenges in learning an optimal policy. The first challenge part is to learn a state representation that can well capture the interactions between the robot and humans in order to inform optimal actions. The second is to consider the temporal evolution of human crowds. We propose to tackle the challenge with the relational graph learning to reason interactions and a model-based RL for far-sighted navigation behavior. Specifically, our method consists of three modules. The first one is a relational graph learning module. We model the crowd of n humans and the robot as a directed graph, where each agent is a node and their interactions or relations are encoded as directed edges between nodes, pointing from agent I to agent J, indicating the amount of attention agent I pays to agent J. This pairwise relation is not known a priori, and it is computed by a Gaussian similarity function, which takes a pair of agents' states as input and outputs the pairwise relation value. If we repeat this for all agents, we obtain a relation matrix of size n plus 1 by n plus 1, which represents pairwise relation embeddings among all agents. A relation matrix is illustrated in this figure, where the thickness of lines indicates the strength of pairwise interactions. After this, a graph convolutional network propagates information from node to node and computes state representations for all agents with the learned relation matrix. Hence, the state representations learned by our method can encode high-order interactions. The learned state representation of the robot and humans are leveraged by subsequent state value prediction and human motion prediction modules. The state value prediction module is a multi-layer perceptron network. It takes into robot state representations and predicts values over a discretized action space. The human motion prediction module predicts future human states, as shown in the subfigure C. Previous works rely on either querying the ground truth or off-the-shelf algorithms to approximate the next human states, which does not benefit from end-to-end learning. The human motion prediction module is modeled by an MLP. It takes the human state feature from the graph convolution outputs to predict their future states. By jointly learning state values and predicting human motions, the policy learning can benefit from encoding future human dynamics and leads to better decision-making ability for challenging scenarios, such as the freezing robot problem, which we will discuss later. The ability to predict human motion allows us to perform multi-step look-ahead planning, taking into account humans' crowds' temporal evolution. We augment the relational graph learning with the simplified Monte Carlo tree search to provide bootstrapped targets of state values in the learning phase and the far-sighted policy at the decision time. Imperfect learned value functions can lead to suboptimal actions due to local minima. To leverage our model's prediction ability, we simulate these steps into the future to provide a better estimate of the state values. Furthermore, by controlling the depth D of this simulation, we can trade off computation for better performance. Our approach is visualized in the tree search diagram as shown in the subfigure D. The planning module performs rollouts using the crowd states prediction and value estimation up to D steps in the future, and select the action with maximum D step predicted return. With D step planning, computation increases exponentially with the search depth and width. Due to our large action space, we use action space clipping to reduce the computational cost. Intuitively, the value function estimates the quality of entering a state. Using this estimate, we recursively search the top W next states with one-step look ahead. Compared to only considering one top action, this step planning promises a better state value estimate when the agent encounters unvisited states. Here we introduce the experiment setup. In this project, we adopt the CrowdNav simulator, where humans are controlled by Orca, and the robot is invisible to humans, which serves as a clean test bed, requiring the robot to navigate through the crowd without affecting their behaviors. One big difference in our simulator setting is we remove the assumption of knowing the human's next states by approximating it with a linear function for baselines. We compare our proposed method to two baseline methods. The first one is Orca, which is an optimization-based collision avoidance algorithm, and the second one is LMSARL, which is an attention-based aerial navigation policy. We trained our model on 10K episodes and tested on 500 episodes. In the end, we showcased our learned policy on a real robot. We train and test our policy in circle crossing scenarios where humans and the robot are randomly placed on a circle of radius 4 meters. The goal location of all agents are on the other side of the circle, and in order to reach the goal, the robot has to fully reason the interactions with and among humans to avoid colliding into them. We report success, collision, extra time to reach goal, which is the rate of the robot reaching its goal without a collision, the rate of a robot colliding with humans, and the extra time to reach goals in seconds, respectively. We refer to our full model as MP-RGL multi-step and the ablation with one-step look-ahead as MP-RGL one-step. We also ablate the whole look-ahead component by using a linear function indicated as RGL linear. Comparing RGL linear to LM-SARL linear, we see that our relational graph learning model is outperforming the one-way attention by capturing high-order interactions among humans. Incorporating one-step look-ahead improves performance and shows the benefits of leveraging human state features with the human motion prediction model. Multi-step look-ahead further boosts performance by looking into the future of a longer horizon and achieves the best performance. Here we show the simulation demos of MP-RGL one-step and MP-RGL multi-step. By looking 4 steps ahead, the MP-RGL multi-step policy anticipates a positive reward for reaching the goal and thus avoids freezing behavior when the state is unvisited. To better understand the benefit of look-ahead with motion prediction, we demonstrate one scenario here by showing the value heat maps of look-ahead model with depth 1 and depth 2. The left figure is the top-down map of the robot and humans, where the star indicates the goal position, and on the right side, the value function for the robot action space is visualized in polar plots, indicating high probability movement directions and speeds with more saturated yellow, and stars indicate the actions of highest probabilities. In this scenario, the value of states in 210 degrees and 45 degrees predicted by one-step look-ahead are similarly high, and the robot chooses to move in the direction of 210 degrees, which leads to collision. In contrast, by looking 2 steps into the future, the robot knows collision is unavoidable for 210 degrees and chooses to move in the opposite direction. We deploy our train policy on a Pioneer robotic platform equipped with an Intel RealSense ZR300 camera and a 2D LiDAR. In this demonstration, the robot navigates through several humans between 2 sides of an empty room. In summary, navigating socially in the crowd requires understanding high-order interactions, and we revisit interaction modeling with relational graph learning. We further model the temporal evolution of human motions, and we show our method outperforms the state-of-the-art RL model both qualitatively and quantitatively. For more details and examples, please check out our project page. Thank you.